G'day, Year 11s. We're going to be looking at the tan function today, and it's one of those ones that we haven't done a lot of, and there are reasons why. And part of it is it's a bit of I think it's an ugly function myself personally. Some people might find it beautiful, but we're actually going to have a whole lot of asymptotes when we look at the tan function, and so it is quite different. So it's a positive slope, the standard one, as long as it has an asymptote of a positive a. It turns at 0 and then continues to proceed up, and will approach pi on 2 but never reach it. We're coming from approaching pi on 2 from a positive side over here, going through 0 and then up this way and repeating. So it is just done through a series of asymptotes. Now, most of the rules that we apply to our standard equations work with tan as well. So if I had y equals, what do we say, a tan n x plus epsilon plus d. Looking at those rules, the a value, now in the sine and cos, it made them a higher absolute, higher maximum, increase the range. A for a tan simply increases the steepness. That's the word I'm going to use if I spell it correctly. The steepness or the slope of the line. Just using purple. So if you think of every value, the y value is bigger, is being made bigger, it means that the slope is steeper. Makes sense? But if it was a half or something like that, and the slope was made smaller, it would be a wider curve. And that's what the a value does. Looking at the other ones, the the period, it works exactly the same. Period changes are the same as sine and cos. The other one, d, works the same. So the vertical translation, what it basically does is it moves the vertical shift is the same method. So basically the halfway point would be either increased or decreased by the factor of d. And epsilon, the horizontal shift, also works the same. So that's an L. Horizontal shift works the same as sine and cos. So when I'm saying works the same, I'm saying the same as what you've seen before. So the techniques are very similar. The only one that really is a big change is the amplitude, and that changes the steepness of the line. Looking back, the asymptote. Okay, looking at question 2b. So I'm going to go through some of the questions now. How do we do this one? So first of all, the amplitude basically means it will be steeper than the average one. And it's basically it's doubled, of course. That's what the 2 means. Not so stressed. Remember, it's a sketch. It's not a portrait. And I also want you to use your graphics calculators or Desmos, but I'm quite happy with the graphics calculators to practice using them because you'll have them in your exams. To draw these, to have a look as you're learning how to do this. Now the period, now it is 3, so the period will be 2 pi over 3. So remember, just like we did in the other, so instead of having 0 pi on 2, pi, 3 pi on 2, and 2 pi, we're going to divide all of them by 3 to show us our points on the graph because the range is from 0 to 2 pi. That's what it says up there. So that becomes pi on 6, pi on 3. Remember, 30 degrees, 60 degrees. What do you think the next one's going to be? 90 degrees, of course. And then 2 pi, 360 divided by that is, of course, 120, which is 2 pi on 3. Can you see what I've done? I've divided everything by 3. 0 and 3 is that. So that tells us our period that we're using. And the other one is that we have a horizontal shift, which is pi on 2 to the left. Okay. Now I'm going to leave this, and like I always do, leave that as the last thing that I'm going to draw. So my x values, my y values, putting in my values, 2 pi, and not 2 pi, it's 2 pi on 3, isn't it? And halfway is pi on 3, pi on 6, and pi on 2. So I will put it in as if this was our case. I'll use purple for our original, remembering that we have the asymptote was at the first and at the third part. Remember, it's a bit steeper, so it would be coming in a fairly steep way, or doubled the steepness, and that's our graph without including the horizontal shift. So we haven't included a horizontal shift. So now I need to move all of those back 3 places. So I'm going to use green to include this. So pi on 2, this asymptote has to move pi on 2 to the left. So it's just as if I'm shifting everything. Remember, every every 2 parts, we have our shift. So if that's pi on 2, it was going up before it, and after pi on 2, it was starting from below. Remember, the pattern is just going up, and so our actual solution is the green value. So you can see that at pi on 2, I shifted to the left. So now I'm using blue, and I'm just going to show that this section after pi on 2, you'll see that it was purple there. And remember, I've said that the green is the true result, so I've moved it. I've moved that whole line pi units to the left. And of course, you'll see that it continues to flow because it is a periodic function and it has recursion. Okay, so the reality is moving pi on 2 to the left is actually turned out to be the same as moving pi on 6 to the right. Another thing to think about. Okay, I hope that is useful. I'm going to delete the blue, and I'm even going to use a rubber to show you what the graph looks like. So the purple is gone. The graph is the green graph. The purple is to show a step in writing it. Okay. I hope that's useful. I'll do some more, of course. Okay, year 11 is just having a look at another one, and we will go with purple for this one. So y equals 3, that's the asymptote, so that means amplitude, sorry. All that means is it's going to be steeper. The period equals 2 pi over 2, which means it's pi, and that is the horizontal shift. So it's pi on 4 to the right. So sketching the graph, we're going to pi, so we have pi on 2, 3/4 pi or 3 pi on 4, and 1/4 pi, which is pi on 4. So I'll take the baseline, the original amplitude. That's actually quite a crooked vertical, isn't it? So I'll just do that. Get a rubber and fix that up. Sorry about that. That's better. And so remember the asymptotes are at 1/4 and 3/4 of the period. The original graph, it is steep because it has an amplitude of 3. The period is halved based on what we see, the fact that the value is 2, and we have a horizontal shift of pi on 4. Because it's negative, it goes to the right. I'll draw in based on the normality of the graph. It normally comes, so it's steep, so I'll do it fairly steep. Going up, going up, and there's your standard tan graph. Tried to make it steep to fit with the asymptote, and that's with that period of pi. But now we realize that all of those values are translated back forward by pi on 4. So everything goes across pi on 4, including the asymptotes. So I'll use green. So the asymptote is pi on 4 to the right. This asymptote is pi on 4 to the right. And of course now the y-axis. So the y-axis is an asymptote. So now the graph will actually look like this. Okay, I'll get the rubber out, so try and take the confusion away. Purple doesn't exist. That was what I used to lead it through to help try to show how it is. I'll get rid of the red asymptotes because they don't exist anymore either. They didn't really exist, they were just used to move. And that's our graph. I hope that was useful. Looking at question 4, there's two real key elements here. The reality is we're working with tan of 2x. So if we're told x is an element of negative pi to 2 pi, we're now looking at 2x being between negative 2 pi and 2 pi. We're going to end up with 4 different answers to this question. Now I have root 3, which tells me that it is in the 60-30 or the pi on 3, pi on 6. So 60 is pi on 3, 30 pi on 6, 1, 2, root 3. It's that triangle, tan being opposite over adjacent. We can see that it relates to the value of pi on 3. That gives me a value of root 3. I'm going to do my unit circle. So remember 0, pi on 2, pi, 3 pi on 2, and 2 pi. But we also have negative pi, pi on 2, if we go back the other way, negative pi, negative 3 pi on 2, and negative 2 pi. Remembering negative goes in the reverse direction. So with that all being said, it's actually not that bad. All stops to central. Where is tan positive? Because it's a positive root 3. It is positive in the A and in the T. So there's the value of pi on 3, and there's the value of pi on 3. The angle, this is a refresher, using the unit circle, it's always the angle between the line and the x-axis. So the x-axis is a vital thing to remember. And so I've got to determine it in terms of positive and negative. So here I have pi on 3 is definitely one of my answers. Here, going around to the next one, is pi plus pi on 3. Okay, now if I go, I'll use a different color to demonstrate. Now I'm going in the reverse direction. To get from here going in the reverse direction, that is negative pi plus pi on 3. And now to go all the way around is actually negative 2 pi plus pi on 3. So putting that all together, I have x equals, or 2x equals, pi on 3, 4 pi on 3, that's a 3. Now this is negative 2 pi on 3, and this is negative 5 pi on 3. But of course it's 2x, and I want the answer to be x. I want to find out what the solutions for x is, which means I need to divide everything by 2. Pi on 6, 2 pi on 3, and you divide by 2. Negative pi on 3 divided by 2, and that one divided by 2 is negative 5 pi on 6. Okay, you see the solutions, and that's how it's done. They are a bit of fun. I don't mind those ones. I hope you can enjoy it, and it's a good refresher for you on using the unit circle. Okay, next one. Now, I know that this is taking a little bit longer, but we haven't done much on tan, so it's worth the explanation. I need to solve for x. I'm told x is between 0 and 2 pi, which means that 2x will be an element from 0 to 4 pi. Okay, remember, if x is 0 to 2 pi, 2 times x would be double that range. Well, that's actually the domain. So now let's simplify by saying root 3 equals cos 2x over sine 2x. Now I know that tan theta equals sine theta over cos theta. So I've got that the other way around. So what I'm going to do is flip it over. I've made the root 3 as root 3 over 1. When I flip it, it becomes 1 over root 3, and this becomes sine 2x over cos 2x. And that means that sine 2x over cos 2x, tan 2x equals 1 on root 3. The same triangle is on the other page, 1 and root 3. That means that the 1 is the opposite, okay, using green for opposite, and the root 3 is the adjacent, which means that in this question we're looking at pi on 6 as our key value. So pi on 6 is our key value. The unit circle, we're going to go from 0 to 2 pi, which is also 4 pi, so we've got to do a double loop. All stops to central. Is it positive or negative? It's positive, which tells me that it's in the first quadrant and the third quadrant. So here is pi on 6. Here is also pi on 6. So that means that 2x will equal pi on 6. It will equal pi plus pi on 6. I'll use a different color to show. Now I'm going to say it equals 2 pi plus pi on 6. And the last one, I'll use purple, we're going to go loopity loopity loop, which actually gives me a value of 3 pi plus pi on 6. That gives me all my variations. So then 2x equals pi on 6 plus 7 pi on 6 plus 2 pi on 6. 2 pi is 12 pi on 6, so that's 13 pi on 6. And 3 6s are 18, so 18 pi on 6 plus pi is 19 pi on 6. I put plus signs in because I'm a dill. I'm not adding them. They are all separate solutions. And so that's a comma. But remember, that's 2x. So that means x will equal those divided by 2. So pi on 12, 7 pi on 12, 13 pi on 12, and 19 pi on 12. And that's our solutions. Okay, enjoy.